Morning chemistry folks, here's just what 14.4 is about. It is about colligative property. Colligative means property of things working together in relation to each other. So once again, colligative property of physical property, it does not change the chemical into anything new. It just changes the way it looks, behave, or its shape. Okay. So an electrolyte, when it ionizes, it breaks up into individual ions most of the time. So for example, salt is NaCl. When it ionizes, it becomes sodium Na ion, and then chloride Cl ion. And your body needs the electrolyte to work to help stabilize your body electronically, and in some cases to make acid, because hydrochloric acid in your stomach needs chloride ion. Okay. And there's usually two type of electrolyte. There are those that are what we call strong. They completely ionize, like strong acid, strong base, and most salt. And then there are some that partially ionize, like certain weaker acid and weaker base. So when you're dealing with a strong electrolyte, you basically get 100% ionization. So if I have 2 mole of MgCl2, when it ionize, it'll break up into Mg and then 2Cl. So 2 times a total of 3 of those, 1 Mg plus 2 Cl, will become 6 mole of ion. Just a review, molality is mole of solute divided by kilogram of solvent. That means just the liquid or the majority substance, not the total mixture. Solvent is just the majority substance. So in the glass of salt water, the solvent is the water, not the salt water, okay? And then the solute, of course, is the salt. The reason why you need to know that is in a little bit when we go back to doing calculation, we're going to use molality. Vapor pressure lowering is the ability of a dissolved particle to make it harder for the solvent to evaporate, so you have less vapor pressure. And it doesn't really matter based on the size of the property. The size of the particle, the solute. It's just more based on the number of solute particle total. So sugar, when it dissolves like fructose or glucose, it's just one molecule of itself. So you have 1 mole of that, you get 1 mole. But if I have 1 mole of MgCl2, I will get 3 mole of ion. And then if I have 1 mole of Na, I would have 2 mole of ion. So MgCl2 would probably have the highest number of particle and therefore has the greatest ability to lower the pressure of that solvent. So the key math for this unit is called boiling point elevation and freezing point depression. Elevation means you add it to the boiling point, and depression means you minus or subtract it from the boiling point. Delta B, TB means just the change in the boiling temperature. KB is a unique number that's given for every single solvent. For water, it's 0.51 degrees Celsius for every molal. And then, of course, M is molality that we reviewed just a little bit earlier. The equation is delta TB equal KBM. So I'm going to grab that and bring. So what is the new boiling point temperature of an aqueous solution? Aqueous means it's water-based if the molality is 5. Okay, so we quickly go back here and we're looking over to the next one. Italicize M. I don't know delta TB and it's already by itself, so I can just plug things in. Okay, and KB is 0.51 degrees Celsius over molal times the molality, which is 5.0. The M cancel out with each other because one is on top, one is in the bottom. And I grab my calculator, go 0.51 times 5, and I get delta TB equal 2.55 degrees Celsius. Here's the biggest mistake from the past. People think that's where it ends. It doesn't, because this is elevation. What's the new boiling temperature, not what is the change in temperature. So the equation gives you the change, but you need to know that water boils at 100 degrees plus the change. So in this case, it'll be 102.55 degrees Celsius. Okay, if you can watch the animation on this, if you do a presentation mode, you can see the green and the blue on the surface will prevent water from evaporating slower. So salt water will evaporate slower than pure water. And that's once again vapor pressure point being lower because of the solute blocking the surface. Okay. So by adding salt or sugar to water, it makes it harder for it to boil. That's why it boils at a higher temperature. You need more energy or more temperature to get something boiling. That's why it's called boiling point elevation, because it's harder to boil. Okay. Here's the opposite, is make it harder for something to freeze, because you have dissolved material getting in between you. You can't crystallize, you can't bond with each other, and this is called the freezing point depression. So you subtract it from a normal freezing point. Normal freezing point for water is 0 degrees Celsius, and Kf is 1.86. Straightforward, you can just read that. So once again, delta Tf is equal to Kf times molality. Okay, and for water it is 1.86 degree per molal. Okay. What is the change in freezing point temperature? Okay, if the change is freezing point in temperature is 4 degrees, what is the molality? So here I'm trying to find M. That is my goal. So the change in temperature is 4 degrees Celsius equal Kf, which is always 1.86 for aqueous, would mean water-based solution, times the molality, we'll call that X, so you are used to that. Now I can cancel the degrees Celsius. Okay, now I have 1.86 next to X. I don't want to get rid of that, so I divide it by 1.86 over M. I cancel that out. But whatever I do on one side, I do onto the other side. So now I have 4 divided by 1.86, and I get 2.15, okay? And then that M being in the bottom of a bottom brings it to the top. It's like a double negative, become a positive. So the molality is 2.15, and X represented molality, and we have our answer, all. Last one, it only asks for the change in temperature, so I don't have to subtract it from 0 or anything, because it's looking for the actual just delta. Okay. This one is, what is the new freezing point? So that, okay. What is the new freezing point of a solution that has a molality of 3.19? So once again, delta Tf equal Kf. So it's Kf times molality. We have a different Kf right here, and we have a different temperature. It normally freezes at -56, so I know this is the temperature of freezing. I know this is the Kf, and I am given molality, which is M. Okay, so I have M, I have Kf. I need to find delta T then, because that's the only thing that's not given. So delta Tf is equal to Kf, which is 1.27 degrees Celsius over molality, times molality, which is 3.9 degree, actually, no, I'm sorry, 3.9 molal. So the molality cancels out. So I take 1.27 times 3.9, and I end up with delta Tf equal 4.953 degrees Celsius. That's the change in temperature, and this is called freezing point depression. So that means we have to subtract it from the normal freezing temperature. So the normal freezing temperature is -56.2. Normally, and we're going to have to subtract 4.953 degrees Celsius. So the new temperature of freezing, after we added this solute into it, is -56.2 minus 4.953, and my calculator tells me -61.153 degrees Celsius. Okay, so normally it freezes at -56, but by dissolving a salt or a mineral or an acid or a base or an oil or an alcohol to it, it makes it harder to freeze, and it drops down to -61 degrees. So freezing point depression is often used to make windshield washer fluid antifreeze for car and things like that. But there's another colligative property of solute affecting the solvent, and that's called osmotic pressure. So osmosis normally happens as things travel through any membrane that's semi-permeable. That means some part can go through it, some part cannot go through it. is being used a lot more in modern day society because fresh water supply in some area in the world is changing, and therefore people have to use salt water to get drinking water and water for gardening and other things. So reverse osmosis is actually technology that's being highly used in the last 5 or 6 years, especially in the Middle East, using the knowledge of osmotic pressure. So without this, um, thousands of people would need drinking water that would not have it. So they are able to get it from seawater now. So with the homework for today, it is pretty laid out. I already give you the equation and stuff. So remember, molality is mole of solute over kilogram of solvent. Okay, so just FYI, 1 liter equal 1 kilogram for water. Water is 1 liter equal 1 kilogram. So with that, you should know the mass of the water is 2 liter, aka 2 kilogram. Okay, and then you already have the mole, so you have to figure out the molality first, and then you have to plug that in there. Now, with that, once you have the molality, you need to multiply it by 2 because for salt, when you dissolve it, it becomes NaNCl. Okay. So here, you're trying to find out what is the molality, and you're given Kb already, and you're given the normal boiling temperature of water is 100 degrees, but now it's 102, so you know the temperature change is 2 degrees Celsius. This one related to osmotic pressure, so read up on osmosis a little bit. But let's just say if I have an egg in salt water, it has a semi-permeable membrane. The salt water is high in concentration of the solute than say the egg. If it's very concentrated salt water, the egg will actually shrink because the water inside the egg would go to where there's less water, which is in the salt water. And the opposite is probably true. If I put an egg in pure water for a long time, the egg will swell up a little bit if you just have the membrane without the shell. Okay, and so water will go to wherever the side that has less water in the concentration. So the saltier side will have the water flow into it. Okay, so just know that your cell is based on salt water, so there's more salt dissolved in your cell than pure water, so it's less water in your cell. Okay, and then if you put pure water in your vein, think about it, it's 100% water, what would happen?